Welcome guys to this vodcast on exercise 15C and D. Now these two exercises are really only preliminary concepts building to 15E, the central limit theorem, which will be our main focus in your next lesson. Now we're also going to help you guys out who do methods at the same time, distinguishing p hat, the sampling proportion, from x bar, the distribution of sample means. Okay, so one is related to categorical data that you'll find in your methods course, and one is numerical data, means in other words, and that's what you'll find in your spec course. All right, now this is a question you might have even asked in your methods course. Something like, what is the proportion of Australian voters who currently prefer Mr. Morrison's ScoMo to Mr. Shorten as Prime Minister of Australia? Now, how do we know? We can't actually go to every single eligible voter and get a definitive answer and then come up with the answer to the question. Polls occur all the time. Once a week even, you'll get a new poll over preferred Prime Minister. So how is this done? Firstly, let's distinguish the concepts of population from sample. A population in this particular context would be the set of all eligible voters in Australia who could make a determination on whether they prefer Morrison or Shorten as PM. Okay, so that's something fixed but really unknowable in this situation. But what we do is, what the pollsters do, the people who organise polls, is they get a sample that is reflective of the general population, all its various demographics, socioeconomic, all kinds of different backgrounds, and it's a real science/art into determining a sample size large enough and represent and appropriately representative of the Australian community that they could sample and have some confidence that this is reflective of the proportion in the population. So they try to make inferences from a sample that they can actually obtain information about to the wider population at hand. Okay, so in the previous example of drawing a sample to make inferences about preferred Prime Minister in Australia, it's quite a complex process. You've got to get a sample quite large and representative of the general Australian community so that you can have confidence of what your sample is suggesting is representative in the wider community, in the population. Now, the simplest form of random sampling is to enumerate, number off all members in the population and get a random number generator, print it off, create enough random numbers to create a subset of the whole population, and then you start to make your poll those people randomly selected that way. So that would be one way of randomly selecting a sample drawn from a large population, is to do it via a random number generator. Okay, so look, here's a very contrived example. We've got 50 students who go to ABC Secondary College. This is an example from your textbook. Exactly 25 males, 25 females. And what we want to know is we've recorded their gender, their sex, and their IQ. Okay. Now what we're going to do is try to draw inferences about the ABC population by taking samples of 5 from that population of 50. Now it's very contrived. Obviously, with a number as low as 50, you can work out exactly what you need to do, because drawing 50 students together, work out the average IQ perhaps of the students at ABC would be easy enough to do. But let's just use this example of thinking about a population with many millions perhaps, and it's just not feasible to be able to poll or get data from such a large population. So we're forced to look at a smaller sample. But okay, so here's our example. We've got our 50 students and we want to randomly select 5 from that population of 50. So I'm going to click over to the next screen. This is what your CAS can do for you. You can go to the catalog, go to R, there's a whole bunch of functions involving random number generation, and I've just chosen rand list. So 5, I want it to select 5 random numbers drawn from a list of 1 to 50, and there we go. So I've just hit that 3 times, and it's a quick way to generate random samples of 5 from that 50. Okay, now you might be wondering, what the hell are we doing here? This is in fact part of the study design of this particular unit, but in no way is it really a testable concept. No way would you be asked to create random samples from a larger list in a test situation, but this is why we're doing it via vodcast, so we don't use our valuable time, class time, talking about this. Okay, we need to make an important distinction, and this is again a methods concept between P and P hat. So if we're sampling to work out the proportion that are female, perhaps, we know it's a fact that there are 25 females out of the population of 50, so the population proportion of females is exactly 0.5. Okay, and that's the population proportion, and we use the pronumeral P for it. Now, suppose we couldn't possibly get round to all those 50 students for a reason I'm not particularly sure, but let's just suppose, and we had to make an inference by randomly selecting lots of 5. Now, the proportion of females in our randomly selected samples of 5 would be P hat, okay? And that's the sample proportion. So we've chosen 5 as our sample size for reasons that are undisclosed to us, but the proportion of females in that sample of 5 is known as marked as an example of P hat. So number in the sample with that attribute over the sample size is how you would work it out. Okay, P hat is literally called P hat, as you can see. Okay, one question you might be asking yourself, if I'm getting selections of 5, random samples of 5, and trying to draw inferences about the population with that particular proportion who have that attribute, is that a problem? I mean, clearly choosing 5, I'm going to get values of 0.4, so 2 out of 5 being female, or 3 out of 5 being female, 0.6 or 0.8 or 0.2, and none of them are equal to 0.5, which is the proportion of females in the population. So is that a problem? And the answer is no, because what we do is we get a whole bunch of samples of size 5, and we start to see that they begin, the more and more samples of randomly generated samples of 5 we look at to try to make inferences about the population proportion, the more and more they'll start to cluster around the actual population proportion P. So we might have a 0.2 and then a 0.6 and then a 0.8 and then a 0.4, and the more and more we get, you'll see there'll be a pattern forming. They'll start to cluster around a center, and that center will be the population proportion 0.5. That's something we'll be looking at shortly. But there's also this idea of when we start to look at numerical data, so in that list of 50 students, there was each an IQ, and we suppose we wanted to look at the mean IQ level of students in secondary college A, B, C. What we do is use the Greek letter mu. Now, IQ testing is always designed to have a mean of 100 and a standard deviation of 15, but suppose that in this particular ABC college, being a typical school, the mean is actually equal to 100, then we mark that value with the Greek letter mu. All right, so that's called the population mean. So if we were to add all their 50 IQ values in that one example, divided by 50, the population size would arrive at the population mean. This is something you could do quite easily, but suppose we're interested in the average IQ of Victorian high school students or Victorian year 12 students. We couldn't possibly go around and collect that information of getting everyone to sit an IQ test. But what we might do is draw a sample, a random sample of Victorian Year 12 students, and start to work out the sample mean, as it's called, and then draw inferences about the wider population, which would be Victorian school students. So we use mu to be the population mean. Okay, so how does the mean IQ of your sample compare to the population mean mu, and what would you'd expect it to be the same? Of course not. All right, so we'll just keep going. So the sample mean, we use a different notation. We use p hat for sample proportion versus p for the population proportion. We use mu, the notation for population mean. We use x bar for the sample mean. So if we're only drawing students of samples of size 5 from the student population, we work out the average IQ of those 5. What we've done is create a value for x bar. So how does x bar compare to mu? 100. And again, it's the same situation. The more and more samples of size 5 that we work out the average IQ for, we expect them more and more to start to center around the population mean, which we know to be 100. So in summary, the population proportion P and the population mean mu are what we call population parameters. And in the ABC example, their values we could actually determine definitively, but in most cases of sampling and statistics, we can't possibly go around and survey everyone or measure everything in order to work out those population parameters. But then we have sample statistics. So we've got p hat for proportions, and we've got x bar when we're looking at numerical data and averages. So, and they're what we can use, what we can determine to draw inferences about our population parameters. Okay, good. All right, guys, so this should help actually those doing methods 3-4 this year. So in the final leg of your unit on probability and statistics, you've discussed this idea of a sampling distribution p hat. And whilst it seems like this is quite a brand new concept, it's really very, very close to discrete and continuous random variables x, and it's a very, very small step indeed from what you've studied previously. So how so? Okay, let's consider this example. Okay, in this situation, you've got 4 white balls and 6 black balls, and we're making 3 selections with replacement. Okay, so you've seen this example before. X we'll call the number of white balls drawn. So probability of success 0.4. N, the number of selections made is 3. It's a binomial setup. So we can create a probability distribution for this scenario. We could have anywhere from 0 white balls up to 3, and we can work out those probabilities quite neatly with our binom PDF in our calculators. Okay, so what we're going to do is use those quite familiar scenarios and just change our perspective and use the language of statistics. So we interpret this in terms of selecting samples of size 3 rather than making 3 selections from our proportion of 10 balls. And what the statistician is interested in is the proportion p hat of each of those samples. So it's a very small step from that table you see before you. So guys, here's the change in focus. You're going to go from your random variable x for number of selections of white ball from 3 trials to this idea of p hat, which is the proportion in our samples of 3 that are white balls, that has that particular characteristic of being white. So this is how you modify the table. It's as simple as that. So rather than talking about 0 white balls or 1 white ball or 3 white balls, it's 1 out of 3, it's 2 out of 3, it's 0 out of 3, it's 3 out of 3. Okay, and our notation changes from x is being drawn from big X, our random variable x, to lowercase to p hat is drawn from the sampling proportion uppercase p hat, and that's it. That's the sum difference. So the probability that one white ball is selected from the 3 trials, the probability that X is 1 is exactly the same thing as the probability of P hat being 1/3. So it's hardly any difference at all from what you were doing previously. All right, guys, 15C deals a lot with the idea of simulating sampling distributions. And it's nothing that would be ever tested or testable in a SAC or an exam situation, but it is something you should know about because it does appear part of the study design. And so it's perfectly covered via a vodcast, and that's what we're going to do now. All right, so this is an example that may well be in your methods textbook. It's the number of people with blue eyes in Finland. So we kind of, well, I guess we could go around and count the number of people in Finland who have blue eyes and divide by their total and get the sample proportion, but it's nothing you could actually do in reality with all the practical constraints that involves. So what can we do? We can get sample size of 100, so we can get lots of 100 Finnish people and work out the proportion that each sample of 100, what proportion contains people with blue eyes. So you can see what happens here. So the upper graph represents just 10 samples of size 100. So you've got people, it looked like one sample had as many as 65 people with blue eyes, another one might have had as low as 52, etc. It's a bit scattered. Let's now take 100 samples of size 100. And then we're starting to see a bit of a pattern. There's starting to get a bit of a cluster going. It seems to be centering around that 0.55. Let's go now another order of magnitude, 1,000, and you can see a much better picture is emerging. We're getting clearly quite a clustering around that 0.55, and so we can have some confidence the more samples we have of size 100 that it's going to start to center around P, the actual proportion of people in Finland who have blue eyes. And of course with 10,000 we get an even smoother shape. So with a larger and larger number of samples taken, the distribution of P hat becomes increasingly smooth and symmetrical and centers on P, the population proportion. Okay, so what other factors could help us gain an insight into P, the population proportion, as drawn from samples? So this time we're going to leave the number of samples fixed. So we're not going to go from 10 to 100 to 1,000 to 10,000. We're going to say we're going to just have 200 samples. But now we're going to vary the other parameter, if you will, and that's the actual people involved in each sample. So sample sizes of 20 to 50 to 200. Okay, and we're going to take out the proportion of those samples of people with blue eyes. So here it is. So if we're taking lots of 20 Finnish people, we get the following distribution. You can see in that the first row. The second row, we're taking a larger sample size of 50, and we're sort of getting a clearer pattern of what's going on. And at 200, an even clearer picture. It's clustering tighter and tighter around that magical 0.55 mark, giving us greater and greater confidence that it's the center of that distribution is in fact the population proportion. So hopefully that should be clear from that. So with larger and larger sample sizes, the spread of P hat decreases and gets closer and closer to the average. So if the center of it gets closer and closer to P. So hopefully that's making sense. Okay, now it's really time to that's linking in with what you've been studying in methods. How does SPECH differentiate itself? Well, rather than look at sample proportions and the idea of categories or attributes such as preferred prime minister or has blue eyes, we're going to look at a different data, ones with numerical attributes like IQ, weight, height, and what we're going to do is mark them quite differently and work out their centers using sample means rather than sample proportions. And that's effectively the difference between what the statistics you do in methods and the statistics you do in Spech. All right, guys, let's suppose we've just grabbed 1,000 people at random from the general community, tested their IQ, and marked where they are, or collected all the results and summarized it via a histogram. You'd expect a shape pretty similar to that in one way or another. Okay, so what characteristics does that histogram have? Well, it's symmetrical around a center. It's bell-shaped. In other words, it's going to be a normal distribution. And in fact, the IQ test is designed to have a center of 100 and a standard deviation of 15. So 15 above, 15 below. So from 85 to 115 covers 68% of people, so on and so forth. So if your IQ of 115, you're at the top 16% and so on and so forth. So all right, so that's what you'd expect to have. What would we expect if we were to take samples from the population? Not 1,000, that's a lot of people, but if we were to take samples of, say, 20 from the population and a whole bunch of samples of 20 got their average IQ, what would we expect that distribution to look like? All right, so that's where we're going next. All right, now one way to answer that question is to simulate the data, and we can do that using our Casio, in fact, which is quite a clever device. So if you go into your spreadsheet application, and what we're going to do is use rand norm. So focus on that for a minute. You don't actually have to do this unless you really want to. So what this is doing is generating 25 randomly selected values out of a normal distribution with center 100 and standard deviation 15. So it's randomly selecting 25 values with those particular parameters involved, and then we're going to be asking to take the mean of it. Okay, and that's going to be the first one. So looking at that first member of the cell, it's pretty close to 102. The next one, as you can see below it, is 99.45 and so on and so forth. So what it's doing is simulating sample means, and it's collecting a whole bunch of sample means together in this histogram that you see over here. And the larger number of sample means, the should reveal a pattern that we can start to draw inferences about. So it's part of your study design. It's definitely not testable, any of this, but it's the idea that you can simulate probability distributions using a CAS and the features it has. All right, guys, so if we wanted to work out, say, the population's IQ, we could do what we did before. We could just get one huge sample size of 1,000, and we could put them onto a histogram and see how they see its center and see its standard deviation, and we can start to work out some, using those sample statistics, make some inferences about the population. Now, another way to go is to actually take, say, 100 or 200, say 100 different samples, maybe smaller samples of, say, 25 or 100, work out the averages for each of those samples, and then start to plot them and see if we can see a pattern. And that's what we're doing here. But what we want to do is, say, fix the number of samples we take as, say, 100. I haven't counted all those dots. Say each of those represent 100 different samples, and think about the effect of the sample size. So if we're going to take 25 people, get them to sit an IQ test and work out the average, that would be one dot in the first graph. And we're going to do that 100 times. So 100 times 25, that's 2,500 different people would be sitting a test, but as broken down into lots of 25. In the second one, we're going to take 100 times 100, 10,000 people are involved, but every particular dot is an average drawn from 100 people sitting the IQ test. So 100 people sit the IQ test, we work out its average, that becomes one of the dots that you see on that probability on that distribution. Now we're going to go even larger. We're going to take samples of 200. So we're going to get 200 people to sit an IQ test. We work out the average of each of their scores. It becomes a dot that contributes to that bottom table. And we do that again 100 different times. So 200 times 100, that's a bucket load of test sitting, isn't it? But then we get a distribution. But you can see the effect of the sample size on the distribution. We get a better sense of the average for the population, and we get a better sense of the actual, well, in fact, it starts to cluster around. So we get less spread, and they start to cluster around the actual average of the population. Interesting. All right, let's have a look at this table. It's entirely fictional, but it's quite believable, and you could generate similar statistics using your CAS calculators via simulation. Not exactly the same, of course, but similar kind of statistics. All right, suppose let's have a look at the first column, and we're talking about samples of size 25. Now we know the mean, so the next row in that table is the mean. We're expecting our IQ test to have a mean of 100, regardless of whether it's sample sizes of 25, 100, 200, or 10,000. The mean, the population mean is the population mean. All right, but what we're going to do is for each sample size of 25, we're going to work out the average IQ. And we're going to do that a whole bunch of times, maybe 50 or 100 times. For each of those different times that we work out the average, we're going to get a further average, and that's what's the average of the averages, if you like, is that next line in of the population. So what we're doing is that becomes the center of our sampling distribution. Our sampling distribution is determined from samples of size 25. And as it turns out, if we look at that distribution of sample means drawn on samples of 25, it's reasonably spread from its center. It has a reasonable spread of 3.05. It's centered on 99.25. Now, if we were to increase the size of our sample by a factor of 4 to 100, so 100 people are sitting the IQ test, we work out the average IQ across the 100, and then we do that a whole bunch of times. What we find is it starts to center around a value closer to the population mean. So this differed by 0.76. This is now differing by 0.24. So it's closer and closer to the population mean. Furthermore, you can see that the standard deviation across that sampling distribution is narrower. So there's less spread. There's more cluster around the center of the distribution. So it has less spread, and the center of the distribution is getting closer and closer to the actual population mean. We go up another, so now we're dealing with 200 people. Okay, you can see in this particular simulated set of simulated values, we're very, very close indeed to the population mean. Differs only by 0.03. Okay, and further than that, there's even a tighter clustering around the center. So we can draw some conclusions about that, and they are, as you see, let me just get rid of this pen. Okay, when the population mean is not known, the sample mean X bar can be used to estimate the parameter, and the larger the sample used to calculate the sample mean, the more confident we can be that it'll provide a good estimate. So there we go. All right, and the more samples we have, the closer it'll be, as well as the larger the sample size. So both work in cahoots. All right, guys, so this next section is the final build up into the central limit theorem, and that's given a probability distribution for a normal random variable x. As we know, such a distribution would be marked entirely by its mean and its standard deviation. What would be the distribution look like if we took samples of size n, so call them x bar, and plotted them all on an axis and observed its distribution? Now, such a distribution is called the sampling distribution, and it relates to the original normal random variable x via the use of the bar across the top. So x bar would be the notation we'd use to mark the sampling distribution that relates to the normal random variable x. So in order to see where we go with this unit, we're going to draw on a couple of pieces of knowledge we picked up from exercise 15b. Firstly, if x and y are normal random variables, we know that any linear combination of x and y is also a normal random variable. So that means our x bar, we're expecting our sampling distribution to also be a normal distribution. And we're going to draw on these properties of the, if x and y are independent, then those properties hold, as we know. Okay, so let's start to look at the very simple case of samples of size 2, and then we're going to generalize them to samples of size n in the general case. So suppose, again, reverting back to the IQ case, which is a case we're going to commonly look at from here on in, we're going to take 2 people that become tested, and we're going to work out their averages. So let x1 be the person, let the IQ of a person randomly selected from the population, x2 the IQ of another, and what we're going to look at is the higher order random variable x1 plus x2. So 2 randomly selected people from this particular population, a population with a mean of 100 and a standard deviation of 15. So x bar in this instance is their average. So the score from x1, the score from x2 divided by 2, as we know, that's an average for size 2. And we can work out its expected value of this higher order random variable x bar. And drawing on a property that we've seen before, half gets factored out the front. And of course, expected value of x1 plus 2 is expected value of x1 plus expected value of x2, which we're going to rebadge as mu in each case, leading to an expected value of mu, which, as we know, is equal to 100. Now for variance, of course, the variance of this higher order random variable x bar is x1 plus x2. Using that property for variance, half as a common multiple of x1 and x2 becomes half squared outside. So it's a quarter variance of x1 plus variance of x2, a quarter of, which leads to the variance of x divided by 2, or sigma squared divided by 2. All right, so for x bar, for this sampling distribution x bar of samples of size 2, we've got our expected value. Our expected mean value between the two is equal to the expected value of the population, which is 100, but the standard deviation is the standard deviation of the population divided by root 2. So in other words, it's 15 divided by root 2, and that's an interesting gain that we've made in our transitioning from x, our random variable of people who are tested for their IQ across the population, to x bar, when we're taking 2 people drawn from the population and working out their average, creating a sample mean from samples of size 2. Okay, guys, there's nothing like a question to try to solidify all this abstract knowledge. So suppose that an IQ in a certain population is a normally distributed random variable x. A reasonable assumption, mean is 100, standard deviation is equal to 15. Find the probability that a randomly selected individual has an IQ greater than 115. Well, we've got our calculators to work it out. We know it's approximately going to be 0.16, okay, because it's 16% roughly lies at the, but our calculators can work it out exactly using norm CDF. Now here's part B. Find the probability that the mean IQ of 2 randomly selected individuals is greater, the mean IQ, the average between 2 randomly selected, is greater than 115. Interesting. Would you think it's more likely or less likely? Have a think about that before we look at what to do for these different calculations. So clearly for part A, it's just that straight out norm CDF, 115, probability that x is greater than 115. I might even mark that down. Let's just grab our pen. So this is, of course, the probability that x is greater than 115, where x is a randomly selected person from the population. And this is, of course, the probability that x bar is greater than 115. Okay, and x bar is the sampling distribution. So where we take particular sample means and we determine them by taking two members from population X, working out their scores, adding them and dividing by 2, working out the mean score across samples of size n. And in this particular case, it's equal to 2. So how is the calculation different? Well, you can see above exactly the same mean. So a mean of 100, a mean of 100. But I now need to adjust the standard deviation, the spread. We're expecting less spread for samples of size 2. So we take the standard deviation from the population and divide it by the square root of 2. Why 2? Because that's the sample size. And of course, you're expecting a much less chance of that occurring. So in fact, it turns out to be only 7.86%. So just to highlight, here's our mean. There's 100. We know 115 lies here. So in the first instance, we worked out the area under the curve x greater than 115. And that's what it turned out to be. It turned out to be roughly 0.1587, we'll say, approximately. But let's now use the sampling distribution x bar, okay, where we're taking two members for that population. Oh, let's just undo that. Hang on, let me just get that erased. That was dreadfully drawn. Let's try that again. Okay, so it'll be the same mean, but the standard deviation will be, in fact, let me just redraw that again. Let's just redraw that. Okay, let's try that again. It should look a whole lot tighter than what it did before. So now each standard deviation is not 15, but 15 on root 2. So that's 100 plus 15 on root 2. 1.4, so it's obviously going to be quite a bit less. It'll be about 110, and here's 115 over here, and it's going to be a much lesser probability. So it's more at the tail end of our distribution for x bar than what it is in our distribution for x, and that turns out to be a probability of 0.0787. So quite a difference there. All right, so what we're doing is in the first case, we're working out the probability using our norm CDF for the random variable x, and in the second case, using our norm CDF for the random variable x bar, where x bar is representing the distribution of sample means of size 2. So hopefully that's clear enough. Compare answers to part A and part B. Let's just get rid of all of that. Okay, compare answers to part A and part B. Of course, it's less likely that the average result from a sample size of 2 will be greater than 115 than it is for a single instance of probability being greater than 115 from the distribution X. So let's see what the actual, hang on. Okay, the probability that the mean IQ of a sample of size 2 will be greater than 115 is much smaller than the probability that an individual will have an IQ of greater than 115. Makes perfect sense, doesn't it? All right, let's now start to generalize our discussion. So we've got X, our normal random variable, mean mu, standard deviation sigma, and of course X is any numerical measure. It could be IQ scores, it could be time to run 100 meters, it could be weight or height. There'd all be examples of numerical measures which would fit a normal distribution. Okay, so if we're selecting samples of size n, we could think of it as n independent random variables, x1, x2, x3 up to xn, each of which have identical distributions to x. So for instance, in the example we've discussed, suppose we're looking at a sample size of 20 and we're measuring IQ. So we've got 20 people sitting an IQ test. Each of them would be members of a general population with a normal distribution set to a center of 100 and a standard deviation of 15. Okay, now the sample mean is, or the sampling distribution. The sample mean is the term we use to describe capital X bar, so the new higher order random variable derived from our original normal random variable X that's taking n members, n particular instances from X, and dividing it by n to create a sample mean. Okay, now lowercase x bar is simply indicating, as conventional with statistics and probability notation, lowercase x is a member from capital case X bar. Lowercase x bar is a member of capital case X bar. If we look at particular examples, particular people and their scores, or the scores of particular people, say 20, and dividing it by 20 gives us a point estimate or a member of the sample mean, capital X bar. Okay, so what we're going to do in this unit is try to take samples of particular sizes and try to make inferences about the population from which they're drawn, about averages about the population from which they're drawn. Okay, so in the previous example, we looked at samples of size 2. It's an easy step to generalize it to samples of size n. So if we're talking about the sample mean X bar, the expected value of the sample mean, we're taking n members, dividing it by n, using that property of the expected value. We can factor out 1 on n. Each of those individual expected values have an expected value of mu, the population mean. So 1 on n times n mu gives us, of course, mu. So our expected value of x bar is exactly equal to the expected value of x. So I might just mark that in. The expected value of x bar is equal to the expected value of x, which we mark as mu, the population mean. Okay, good. All right, let's go back to this. All right, what about variance? Okay, I might just get rid of that. What about variance? Of course, the variance of our sample mean x bar is x1 plus x2, n instances of members of our original normal random variable x divided by n. Okay, we're using that property of variance. We factor that 1 on n out as a common factor, becomes 1 on n squared. The sum of those 4 variances becomes n times the variance of x. So there it is there. So there's n lots of the variance of x. Oops, n lots of the variance of x, which is all of this. There it is there. Divided by n squared leads us to this general rule. So it's the variance of x divided by n, which of course we use the notation sigma squared for the variance of x. All right, so then therefore to work out the standard deviation, you can guess what we need to do. Let's just move across to the standard deviation. Oops, no. Let's just clear that off. Hang on a minute. Therefore, if sigma is the standard deviation for the numerical variable random variable x, then sigma on the square root of n is the standard deviation for the sampling distribution x bar. Okay, so I'm calling it the sampling distribution. They've called it the sample mean. So maybe I should stick with the notation equivalent to the book. Okay, and this leads us to this conclusion and this preamble leading up to the central limit theorem. So if x is some normally distributed random variable, such as IQ in a population, such as time to run 100 meters, such as height, for instance. They'd all be normally distributed random variables regards to members of a population with a mean mu and a standard deviation sigma. Then the distribution of sample mean x bar, is also going to be normal, okay? And its mean is exactly equal to the mean of the population. But its standard deviation differs. It's equal to the standard deviation of x divided by the square root of the sample size. So that's the key feature when you're moving from members of a normally distributed random variable to averages or means of samples of a particular size. The center remains the same, but it becomes more tightly clustered around the center. It becomes the original standard deviation divided by the square root of the sample size. That is the key understanding. So let's now get into an example. So a simple example. So IQ scores of adults are known to be normally distributed, as we've seen and discussed many times. Mean 100, standard deviation 15. Find the probability that a randomly chosen group of 25 adults will have an average IQ of more than 105. So we're transitioning from X, the population with known mean and standard deviation, to X bar, to the sampling distribution, or to the distribution of sample means, where the sample size in this particular case is equal to 25. So how does that inform our use of norm CDF in being able to calculate the probability that our average IQ will be more than 105? Well, hopefully you're onto it by now. And this is using the correct notation. Probability that X bar is greater than 105 is just norm CDF. Okay, so the lower limit 105, upper limit infinity, and what changes, of course, is the measure of spread. The standard deviation now goes from 15 to 15 divided by 5, or 15 divided by the square root of 25, because we are dealing with X bar and not X anymore in this particular instance, and it turns out to be quite a low probability, 4.8%. Okay, that takes us to the end of this session. It was a little bit long-winded. This is why I wanted it to be a vodcast, so we could avoid all this sort of guff and get into the more meaty maths that comes with this kind of background knowledge. Okay, that's it for now. Enjoy your weekend. I'll see you later. Bye.